Okay, thanks for coming along to this final part before morning tea. So I'm going to be just talking to you about what's below the ground. The talks previous have all been above the surface, so now we're going to look at some things which are happening under the surface. So I'm Don Cherry. I'd like to acknowledge my co-authors in this, John Fawcett and Bruce Gill. We're all members of Future Farming Systems Research Division, which is a research arm of Department of Farming Industries. We're each based at regional centres in Victoria, Bendigo and Tatura, and the other two gentlemen are hydrogeologists. I'm a plain-on geologist. The project that we're working on is a 3-year funded project through National Water Commission and Victorian Water Trust to look at trying to understand how we can model the aquifers and using all the multi-dimensional data that we have in bore data. There's a large historic store of bore logs going back over 150 years to the first holes drilled in the gold era. We've also got a number of pre-digital maps and sections and things, and using that sort of data in new innovative ways using the technology available today. So we're picking up on technology that's been used by minerals and oil industries over the last couple of decades. There's literally dozens of 3D visualisation and modelling packages available to those industries, and we're wanting to explore how to use those for groundwater. We're looking at emulating the work that's been underway in North America and Europe over the last 8 to 10 years, I suppose. There's a strong group in North America who have been modelling groundwater because they rely so heavily on groundwater and less on superficial water. And the end product of that is so that we can better understand our water resources and manage that as such. But in all great projects, we face a number of issues. I mentioned the 150 years of bore logs recorded in Victoria, and they're in multiple databases. There's a minerals exploration database, there's bore water databases, there's databases held by private companies. They're in a whole range of formats, Microsoft products, other web-based systems, custom-built ones. Because of that, there's a multiple range of formats from relational to spreadsheets. There's a heap of information that's missing. We might have bore coordinates, but no log, or we've got log information and we don't know where the bore is located. Or there's even translation errors. We've got all this wonderful information, but the coordinates for the log are actually incorrect, and we'll replace it somewhere in another catchment. And this, with 150 years of logging, we've got a range of styles of interpretation. For example, one logger might describe something as a medium-grained, clean sand that contains a lot of water and have water data. Another log might just describe it as sand. I don't know anything about it. I don't know the quality of the sand or that sort of thing for transmitting water. So how do we manage all of this? Because of all of these types of databases and formats, we've had to do a lot of pre-processing to get that into a georeferenced database in compatible formats. So then can be fed straight into a GIS package. In this case, we use ArcGIS. So we manage the database that way. We do spatial processing to produce rasters, and there's an early stage of visual checking here. Now, all of this data we can visualise in a whole range of different ways. There's a whole heap of things that we can actually visualise. Here, today I'm just talking about how we're using that visualisation to check for errors. We export from ArcGIS to another product called GoCAD, which is geologically oriented computer-aided drafting, which is a great tool for developing and managing 3D objects, and it's grown out of a consortium of organisations worldwide for use in the petroleum industry. So it's well suited for looking at structures that contain water. So we input that data, create surfaces and voxels. If you don't know, voxels are volume pixels. So it's a 3D pixel if you imagine an object like a Lego cube. And then there's another visual processing check stage there, and then that would feed back, if there's errors picked up in this stage, that would feed back to the database for correction. And the sort of data that we have, we've got historic maps, and now we've got the digital versions of those with polygons, polylines and points. We've got a range of cross-sections. This is just a cartoon sample, but there are cross-sections and a wide range of handwritten and typed up and captured bore logs. So in this particular case, we've got depth from and to, and then a short description of what was intersected at that depth. So the study that we're working on is piloted for 3 catchments, the Campaspe, Loddon and Moorabool river catchments in central Victoria. They're important catchments for the communities that are nearby. Bendigo, for example, derives the majority of its water from the Campaspe and the Culloden water system, which is a tributary to the Campaspe. There's other communities along the Loddon which rely heavily on the groundwater, particularly the farming communities. And then we've got Geelong and other communities that rely on the Moorabool groundwater. Just a couple of examples of some of the visualisation products that I've produced so far. The top left is just a standard map out of the ArcGIS. That image and the one below it are parts of the Moorabool study area. The bottom left is actually an oblique view of the 3D surface. The other 2 views are showing the water table in relation to a basalt flow, and then this block diagram down the bottom right. So what sort of errors might we get, and how do we see them? In this triangulated network surface within GoCAD, this was modelled through inverse distance weighting algorithm within ArcGIS, and then exported out as an ASCII text, imported into GoCAD, surface created, and we have this anomaly pop up in the middle of it. We thought, well, that's a bit unusual because most of the rest of that area is undulating. It's quite an unusual thing to be sticking up there, and the surface that's actually being modelled here is bedrock. The red lines here and the little yellow shapes represent drill holes which have been put in and we use to derive this surface. And in this particular case, the culprit is the one with the arrow next to it. It's actually a short borehole. The interpretation by the logger was that it had reached bedrock at a shallow depth. It had gone into a white clay, according to the log. When this anomaly popped up, you wouldn't see it in the table or in the database. It wasn't until it was visualised that its near neighbours are all quite deep, and when I interrogated the logs for its near neighbours, they all passed through a white clay into another aquifer, gravel and sand at a greater depth, and continued down, which shows in this image you can see the greater depth for them. So in this particular case, the anomalous borehole has to be left out from modelling the ground, the bedrock topography, because it's going to impact. And there's other places across the study areas where this has been found. I've just pinched this image from a well-known virtual or digital globe product just to demonstrate how we can visualise topography obliquely. And we have in this image a valley floor, valley sides, a number of tributaries coming into it. We'll come back to it